Hey guys, welcome to lecture number 8, I think. Anyway, at some point I will lose the number or the lecture number, but today I would like to continue with derivatives, and we will see today how to find derivatives of functions using the definition. In fact, I would like to go back to that function. I think it was the square root of 2x plus 3. And then at some point, I would also like to discuss some qualitative properties of the derivatives. You will see what happens if the derivative of a function is positive, not negative, and how is the graph of the derivative related to the graph of the function. And next time, probably I will stick more to the rules of derivatives, how to apply the basic rules like the sum rule, product rule, quotient rule, and so on. All right, let's get started. So like I said, I would like to start with that example. So let me go back to this one here, right? Right. So last time, if I remember correctly, we were on this here. Okay. So the question was how to find the derivative of a function y of x, right? But if you don't like the notation, you can always switch y with f of x if you don't like it. But anyway. In any case, so this is what we need to find out. What is the derivative of this function, square root of 2x plus 3? Well, as you can see here, you have a square root of something. So you have a composition of functions here, right? You compose the function square root of with the linear function 2x plus 3. But anyway, there will be a way to find the derivative of such a function using the chain rule, but we will find out later on. But now let's see. The only tool we have at this point is just the definition. So like I said, let's denote this by f of x. And pay attention here, I would like to say one thing. When you have the square root of something, always think of applying the conjugate at some point. So that's what you, all right, so let's see, let's apply the definition. So keep in mind that the definition, so let me write it here again. So f prime of x will always be the limit as h approaches 0 of f of x plus h minus f of x, everything over h. So that's the definition. Right. So always have this in mind. All right. So by doing so, as you can see, we can express the f of x plus h. So you see you have f of x is 2x, square root of 2x plus 3. So f of x plus h, this guy here, is the square root of, and now I'm going to replace x with x plus h, so it's 2 times x plus h plus 3. And of course, you will find it here. Look at it here. You see it's here. That is f of x plus h, right? And of course, f of x, which is here. All right, so at the end of the day, we need to find this limit right here. So let's see how we're going to do it. We're just going to apply the conjugate. So we're going to multiply by the conjugate. And as you have seen here in a box, so we will get that this is the limit as h approaches 0. So first of all, let's look, what is the conjugate of this? So let me write somewhere here. So we need to find the conjugate. Okay, I'm gonna find the conjugate. So we need to find the conjugate of this guy here, of the square root of, in fact, let me write with a different color. So we need to find the conjugate of the square root of 2 times x plus h plus 3 minus square root of 2x plus 3. So we need to find the conjugate of this. And the way we're going to find the conjugate of this is just by multiplying by the sum of the two square roots, right? So that's what we will do. All right, beautiful. So that's exactly what we're doing here. You look at the conjugate is right here. You see it? This is where it is. So that's the conjugate. So the conjugate of this, which is, the conjugate is exactly this guy here. And of course, we're going to multiply and divide by it. And once we do so, remember, this will be this, we have this identity. Let me say that here, square root of a minus square root of b times square root of a plus square root of b is a minus b. So keep this in mind. So we using this identity, then we're going to end up with this expression here, right here, right? So the square root will just vanish, right? So look at the top. So once we multiply, see, in our case, a is 2 times x plus h plus 3, and b is 2x plus 3. And we have there under the square root, so we have the difference of the square roots times the difference times the sum of the two square roots. And of course, it will be just the difference of the quantities inside the square roots, both square roots. Does this make sense? Okay. And now you're going to see, you're going to end up what here, what you get here at the top, right? So a minus b will be this guy here at the top, right? This guy here, which you can do some basic algebraic operations with this. So at some point you will get this, right? You see, you get this here, which is here. So now by just doing the basic operations, algebraic operations, look here. So just do here basic algebra. Like subtracting whatever. So you work on the numerator. And once you do this, guess what? You will end up with, you see, the 3 will go away, 2x will go away, and you will end up with 2h, but also you have an h here on the bottom. So h will cancel, and then you're going to end up with this guy here. And now what you're going to do, you're going to plug in h to be 0, and guess what? It will give you, the final answer will be this. So the derivative, we're going to write it like this, 2x plus 3 prime is nothing else than just 1 over square root of 2x plus 3. So that's the derivative of this guy. Right? Okay, is it clear for everybody? So once again, the main secret here is just to apply the conjugate. So once you have the conjugate, then everything is just pretty straightforward. So the moral of this problem is that when if you are asked to find the derivative of a function using the definition and you have the square root, that's what you need to do. You need to take into account the conjugate by multiplying by the conjugate. So keep that in mind. Okay, now let's see another problem. So we have something similar. So find the equation of the normal line, whatever that is, we'll find out. So we need to find the equation of the normal line to this curve, y of x equals the square root of 3x plus 1 at the point x equals 1. That's very important here, at this point here. All right, so what do we need to do? So first of all, step one, when you hear everything like find the equation of the tangent line, find the equation of a normal line, at a certain point, you always, step one, you always think of the derivative, of the first derivative of the function, always, right? So in this case, just like we have seen, you need to find the derivative of the function. So in our case, we need to find the derivative of the 3x plus 1. And here we go again. We will apply the definition. In fact, you know what? I would like you to think of it. So this is the definition. Think about it for a minute or two, and maybe you'll tell me what is the derivative of this. So you see, when you apply the definition and you end up with this guy, you have this guy here. And what should we do here? Can you tell me? So we see you have at the top you have the difference of the two square roots, and on the bottom you have h. So what should we do here? Multiply by the conjugate. Yes, indeed. Like Kyle, Muhammad. Oh, Muhammad went already too far and he gave me the derivative. Anyway, yes, that's correct. But anyway, we'll get there. But first, we will multiply by the conjugate. So what is the conjugate of this? So what is the conjugate of this guy here? The conjugate of this is what? Can you tell me? So what is the conjugate of that difference of square roots is what? Exactly. So it will be the square root of 3 times x plus h plus 1 plus the square root of 3x plus 1. So that is the conjugate. So we're going to multiply by this, multiply and divide. You see it here on this side here. So once we multiply, and again we're using the same formula, square root of a minus square root of b times square root of a plus square root of b equals a minus b, right? We're going to end up at the top with this guy here. As you can see, is the same thing, is the difference of the quantities inside the square root, but this time without the square root, which is great for us. That's exactly what we wanted, right? And then on the bottom, you'll have h times the sum of the two square roots. But there is no problem. If you have these at the bottom, then it's great. And now what we need to do is just to do some basic algebraic operations at the top. So by doing this, you see things here will get clearer because you'll have 3x plus 3h plus 3 minus 3x minus 1. And this will give us, you see, as we, so 3x will go away. And sorry, here is 1. I made a mistake here. 1 will just go away. And this will be nothing else than just 3h that you will find here. You see, look. So it's exactly what we did, and you will find it here. And then h with h will cancel, h at the top with h will cancel, and then you're going to end up with this guy here. So we need to find the limit of this. And now, by the same approach, we we're going to end up with, you're going to plug in h to be 0. And this will be, the result will give us 3/2 times square root of 3x plus 1. Right? Okay. So that's the derivative, and I think somebody already gave me the answer. Let me see the chat. Yes, exactly. Yeah, Muhammad. Yeah, exactly. All right, but we're not done yet. Pay attention that we need to find the equation of the normal line at the point x equals 1. So now we have this. So that's the derivative, right? And now the second step is to find the slope of the tangent line. Always when you hear this thing here, the slope of the tangent line, you're always gonna think of the derivative. So the slope of the tangent at the point x equals 1 is nothing else than just the derivative, you see here, evaluated at 1. So this is, and let me be more specific here, in fact, let me write it this way, so that this is the derivative of the square root of 3x plus 1 evaluated at the point x equals 1, you see, and you get it, you're just gonna plug it in. So the derivative, as you can see, is here. So this is nothing else than just 3/2 square root of 3x plus 1 evaluated at x equals 1, which will give us 3/4, right? All right, and then step 3, the slope of the normal line, well, as you can see, at x equals 1 is negative 4/3. Why is that? Can you tell me why? What is the property that the normal line and the tangent line have? I think I said this in one of the, well, it was one of the videos that I told you to look at. But you know this from college algebra. So the normal line and the tangent line have what property? The slopes of the two. That their product is -1, right? They're perpendicular. So you know that they are since they're perpendicular, their slopes, the product of their slopes is -1. So the normal line, the slope of the normal line, right, at x equals 1 is 1/. So you see you have, so it will be -4/3. Because the product is -1. And now you can find the step 4, with that we need to find a point that the normal line goes through. So at x equals 1, you'll plug it in and you'll have that this is nothing else than just the square root of 3 times 1 plus 1, which is 2. So the normal line goes through the point of coordinates 1, 2. So let's keep this in mind. All right, and finally, the equation of the normal line will be nothing else than just, you're gonna write, since the normal line goes through this point, so you see, let's just say that if it has this point, usually it's y minus y0 is the slope times x minus x0, right? So in our case, x0, y0 is 1, 2, and the slope is -4/3. So, and here we go. So that's the equation, right? So once again, you need to follow this step. So first of all, you're asked about the equation of the normal line. So you need to find the slope of the normal line first, because this is how you express the equation. You have to write the slope, and then you have to find a point on such that the normal line goes through. But first, to find the slope of the normal line, you need to find the slope of the tangent line, because you know they're perpendicular, so the product of their slopes is -1. And to find the slope of the tangent line, you need to find, basically, is the derivative evaluated at that point. And here we go. So these are the steps that you need to follow, right? So first, you need to find the derivative. And then you find the slope of the tangent line at that point, which is the derivative evaluated at that point. Then you find the slope of the tangent line. Then from the slope of the tangent line, you find the slope of the normal line. And from there, you have to have a point that the normal line goes through, and then the equation follows immediately. Is it clear for everybody? Does this make sense? Do you have any questions regarding this example? No questions? Okay. All right. So that's what you need to do. All right, now let's talk about the relationship. So let's get towards more qualitative properties of the derivative. So let's talk about the relationship of f and f prime between these. And now let me draw your attention with the following graph. And I would like you to look very closely at it. So look at the graph, and let's look on the left side. You see, this is the graph of the function. Let me just draw it. You look at this here. This is the graph. It goes like this. All right. Okay. All right. So this is the graph of the function. So as you can see, up to some point, the graph rises, right? If you take the tangent line here, so the derivative will be positive. So this is what happens. The graph rises all the way to this point where it basically flattens. So at this, when the graph flattens, you need to know that the derivative will be 0, and then the graph will fall. And when the graph falls, this means that the derivative is negative. So that's here the tangent line to the graph, right? So that's what you need to know. All right, so let's look at the, so at the point, you see at the point x equals 2, the derivative will be 0. You see the maximum point is here, but it's for x equals 2. You see, this is where all this happens. So this is the point 2, right? So at x equals 2, the graph flattens, so you have this information here, that the derivative is actually 0, right? So by the way, I have a question because I received some emails now. If you get kicked out by the internet, please just click again. You can log in at any time. You just put the password for the meeting, and that's it. So you can come back at any time. All right, yeah. So yeah, you can. So don't hesitate. You can come back. You don't need my permission to do so. Okay. So now let's go back. You see, we have the at x equals 2. You see the graph flattens, so the derivative is 0, right? And now for x less than 2, you see on this side here. So these are the values from here to here. In fact, not from here to here, to be honest with you, it's more like from here all the way from, these are the values for each, for x, and these are the values for which x greater than 2 and less than 2. So as you can see, for values less than 2, the graph rises, so the derivative will be positive, as you can see it here. And for x greater than 2, the derivative is negative, so the graph falls. So that's what you need to know. And something will happen. So that's the relationship between the derivative of a function, the first derivative of the function, and the function itself. Okay. Anyway, we will see that there is something going on. If something will happen with the function if the derivative is positive, something will happen if the derivative is 0. We'll call these kind of points in a certain way. I'm not going to tell you for the moment. I'll keep you in suspense. And then for if the derivative is negative, something else will happen. But anyway, we'll get there. Have a little bit of patience and we'll go there. All right. Now let's talk about the graph of the derivative a bit. So the function is increasing at the same rate. Look at the first graph. Look here. If you look at this, this is a line, right, that goes through the origin. So it's a linear function. It goes through the origin here. So this is an increasing function. It increases at the same rate. So the slope of the tangent line, or let's say the derivative. So always when you hear the slope of the tangent line, you are thinking about derivative, is positive and constant. So this is how it's gonna look like, you see, for example. But the derivative will be a constant. It depends on the function, right? If the graph of this function, it is what? It is 1/2 x, something like this, right? So the derivative will be just 1/2, will be the constant, right? As you can see, it's 0.5. So that's the relationship of, this is how we're gonna draw the graph of the derivative. All right. But now we would like to ask a question. When is the function increasing? What can you tell me based on what we have previously seen, right? If I go back to so this is the question, keep the question in mind. That is the question that we would like to ask. When is the function increasing? And look here, look, let's go back to the graph. So based on the relationship between f and f prime, what would you say here? When is the function increasing? Can you tell me? By just looking at the graph. When x is less than 2 is what? Is increasing, right? And when x is greater than 2 is decreasing. So when the graph rises, the function should be increasing. So in our case, the derivative is positive when the graph rises. And when the graph falls, the function is decreasing. So this means that the graph, right, the function, so when the graph falls, the function is decreasing. Okay, that's great. So going back to our question, when is the function increasing? Well, guess what? Or when is the slope of the tangent line positive, basically? So let's look here. So let's look at this function. What would you, this graph? So when f prime of x is positive, when x is less than -2 or greater than -2, what do you think? when x is less than -2, right? Look here, this is -2 here, and this is 2 here, right? What happens to the graph of the function when f is less than -2? So look at it. The graph, what happens to the graph? Can you tell me? The graph rises, so the function increases. And what happens here again? The graph, what happens with the graph here on this portion when x is positive? Again, rises. So maybe it is increasing on both, on both when x is less than -2 and also x greater than negative. So maybe it's both. The derivative will be positive, both, right? Okay. Now, the same thing, when is the function decreasing? And the function decrease will be between these two. You see, if, again, I have here 2, and here I have -2. So as you can see, the graph here falls. So it's decreasing on this interval. So the function is decreasing. Right, and here the function is increasing. So that's what you need to know about these two. Any questions so far? Is everything clear so far? So, all right, I'm glad to hear this then. Please stop me at any time if you have questions. All right, so this is what happens. So keep in mind that when the graph falls, it's decreasing. When the graph rises, it will be increasing. And the way it's going to be related to with the derivative or the slope of the tangent line is when the derivative is negative, then the function will be decreasing. So the graph will falls. And when the derivative is positive, the graph will rise and the function will be increasing. All right. But the question is now, well, what happens when, okay, let me address this question. But what about all the points for which the derivative is 0? We have seen what happens with the derivative positive. We have seen what happens with the derivative negative. But what about with derivative 0? Because as we have seen previously here, right? The graph flattens as well. It's not just going to rise or fall. It can also flatten. So what happens when the graph flattens? So when the graph flattens, the following thing will happen. So let's look. You see, when the graph flattens, we're wondering what kind of points do we have there for which f prime of x equals 0. And we will have something what we will call local min or local max. Local extrema in one point. Or equivalently, we can address, or when is the slope of the tangent line 0, right? Keep in mind the slope of the tangent line is the derivative. And as you can see, the x equals 2 and x equals -2, the derivative is 0. At these 2 points. So this is what we mean, that these 2 points will be either local mean or local max. But anyway, we will decide what kind of, which one is which one. So which one is a local min, which one is a local max. Anyway, we'll see at some point. But let's summarize everything now, and let's put everything together on what we have discussed. So, as you can see from the graph, in this function, right? For example, let's look at the graph of this function. Look at the, you see, let's interpret this. So this goes, it passes through some point here. It will, somewhere here, it will flatten, right? And it will go down. So the graph falls. At some point, it will flatten here as well. And then it goes up. So the graph rises as well. So let's see at what point it's flattening. So let's see, it's somewhere here at 2. And here it's -2. So for values less than -2, you see the graph rises, right? So here the graph rises. So the derivative will be, or the slope of the tangent line will be positive. But also here, the graph rises as well here. And here on this portion, in fact, let me put another color. On this portion here, you see, but only on this portion. So here, the graph falls, right? So, and you can translate this, you see the derivative between -2 and 2, the derivative will be this. And here you can translate this, both of them. This one here, the graph, so the function will be increasing. Oops, sorry about that. Right? All right, so, but now we have another situation. You see, the graph flattens at 2 points, at -2 and 2. So this means that the derivative will be 0 there, right? Let me denote this by another color. So let me put it this way, right? At these 2 points, the graph flattens, and you'll find it right here. And this will be what we will call a local mean or local minima or local maxima. So these 2 points. Right, so once again, so that's the graph of the function f. As you can see, the graph rises all the way to, for the value for which f of -2, whatever that is. And then it will fall between -2 and 2, and then starting from 2 all the way to infinity, it will rise again. So in other words, the derivative will be negative on the interval -infinity, -2. Then it will be, the derivative will be positive, I'm sorry, from this. So from, once again, from -infinity, on the interval -infinity, -2, the derivative is positive. Then between -2 and 2, the derivative is negative, and then starting from 2 all the way up to infinity, it will be positive again. And then you will have some these, what we'll call these critical points at -2 and 2. And of course, so that's the graph of the function. The graph of the derivative, as you can see, it will go, it will pass through -2 and 2, and it will have a minimum somewhere. So it will be a quadratic function. Right, as you can see here. This is the derivative, and you can interpret the graph of this. So that's the f prime. It will have a minimum here. So as you can see, the graph falls all the way to a minimum, and then it rises again. So here the graph falls all the way to this point here, -2, and then the graph rises. All right. Beautiful. So that's the relationship between these two. So let's say one more time. So when is the function increasing, or when is the slope of the tangent line positive? Well, or when is the derivative of the function positive? Let's look again. You see, let's look at this graph. In fact, I would like you to tell, in fact, I want you to look at the graph and maybe you will tell me, when is the derivative positive? Or when is the function increasing? Just look carefully at the graph. Well, which one is it? So let's look again. Look at the graph here. It falls to the point here, and this is -2, you can see. Then the function is what? Rises all the way to some point here at 0, right? Which is for x equals 0. And then it will fall again all the way to some point here, whatever is 2. And then it will rise again. So I'm asking, when is the graph basically, when is the graph rising? That is the question. In other words, let me translate the question. When is the graph rising? On what interval? Let's see the first portion here. Is it rising here? All the way to -2? Not quite. The graph falls. Let's see, from -2 all the way to 0. Is it rising? Exactly. The graph is rising on this portion. So graph rises. I think it was with double S, rises, right? If I remember, no, it's 1S. Yeah, correct. Anyway. And now the graph here falls. Right, all the way to here, and now the graph rises here. So just like, let's see, just like Nolan says, on both. So the graph rises on both, right? When x is greater than 2, and also when x is between -2 and 0, right? All right. So that's when the derivative is positive, is when the graph is rising. And when the graph is falling, the derivative will be negative. So that's what you need to know. Okay. Now let's see a similar situation. Now, what can you tell me here? When is the graph falling, in other words? So that is a question we need to ask. When is the graph falling? That's what we mean by this. Well, what can you say? Let's see, Jake says both -2 when x is less than -2 and x between 0 and 2. Let's see. Yes, indeed. So the graph is falling when on this portion here all the way to so -2. So when x is -2, yes, indeed. So it is falling. And when else is falling? So here it will rise. So it falls from, it's falling from here also all the way to here at x equal 2. So between 0 and 2, right? Again, falling.
I have a question.
Yes.
If there are any like test questions on this, would the format that they've been writing it in chat, would that be how you want us to write it as the answer?
It depends on the test. If it's like an online test, it will be just multiple choice. So you'll have a question and you'll just click which one is correct. But when you have a midterm, you'll need to justify it. How you need to explain why this is falling, why this is rising, and you have to connect them with the derivative. You have to explain. Does it make sense?
Yes.
Cameron? Okay. Any other questions? Please feel free to interrupt me. I'm actually starting to, I want to get used to this being interrupted if you have questions. So it's clear here. So that's what you need to remember. When the graph is falling, the derivative is negative, or the slope of the tangent line is negative. And you can say that the function is decreasing. And the same story, similarly, it holds when the function is increasing, the graph is rising, so the slope of the tangent line is positive, and therefore the derivative is positive. Okay. But now let's say a few words about what happens when the derivative is actually 0. So in other words, we have local extrema, or you can say local max or min. So in other words, when f prime of x is 0, well, just look here. If you see here at 0, at -2, so the graph flattens, and here at 2. So these are the 3 points. So f prime of x is 0 at these 3 points. And we will call these local min or local max. We can call them local extrema. Right, there are 3 of them. Anyway, we'll decide, there will be some a way to decide which one is a local min, local max, but anyway, we will see this more in detail when we will discuss this first derivative test or the second derivative test, or both of them. So you'll see later on in the course. All right. Let's look at the following scenario here. I want you to tell me, well, as you can see, if you look at the graph of this, just look at it. See, the graph falls all the way to this point, -2. Then it rises all the way to 0. Then it falls again all the way to 2, right? And then it rises again. So that's the graph of f. Right, clearly, when x is between -2 and 0, right, on this portion here, the derivative will be positive, right? The graph is rising. So the graph rises. Here graph falls. Again here the graph falls on this portion. And here again the graph is rising. Okay. So now, and also we have that the graph will flatten at these 3 points here, right? As you can see, in fact, let me write this with another color. At these 3 points here, the graph flattens, as you can see here. Other than that, you have this scenario with these things when the graph is rising and when the graph is falling, right? The derivative is positive when the graph is rising, and the derivative will be negative when the graph is falling, right? All right, now how do we draw the graph of the derivative? Well, as you can see, it's gonna go through these points, right? -2, then it will go through 0, and then it will go through 2. So -2, 0, and 2. And again, the same thing will happen, right? Because that's how you, so when the graph is rising for the function f, the derivative will be positive. So make sure the derivative is above the, right? So between, you see, between a negative 2 and 0, in that interval, the derivative is positive. So see here on this portion is positive, which it's above the x-axis, so it's not negative. Then between 0 and 2, if the derivative is negative, is below the x, you see, and then starting from 2 is positive. So this is how you draw the graph of the derivative. I think there are some questions in your homework how to draw the graph of the derivative. So they say given the graph of the function, which one is the graph of the derivative corresponding to the function f. So this is how you interpret them. So you always look when the graph rises, so it will be the derivative is positive. When the graph falls, the derivative is negative, and you also have these points when the graph flattens, and basically the derivative will be right. The derivative will be 0, just like here. Okay. All right. Now let's talk about the existence of derivatives. What guarantees that the derivatives actually exist? So we will call this function that, well, in some sense for which the derivative exists, we'll call this kind of a differentiable function. So that's what we mean by, so this is the set of these derivatives, let's say, well, more or less, is what we call differentiable functions. So in other words, there are functions for which the derivatives basically exist. So a function is differentiable at a point only if the limit which defines the derivative exists there, right? Remember, the limit, so f prime of x was nothing else than the limit as h approaches 0 of the difference quotient, which is f of x plus h minus f of x, everything over h. So that's right? So keep this in mind, which defines the derivative that existed there. But not all the functions are differentiable. There are examples of functions which are not differentiable at certain points. And we'll give a couple of examples. So let's see 3 examples. The first one is a corner point. You see here, and I think I've told you about this function before, f of x is the absolute value of x. This function is not differentiable at the corner point, which in our case is 0. At the point x equals 0. You see here, this corner point is not differentiable. Why is that? Well, if we take the left-hand limit and the right-hand limit, right, and of the difference quotient, you will see that they do not agree. And anyway, let's prove this. Let me explain the proof. So let's prove that the function f of x equals the absolute value of x is not differentiable at the point x equals 0. You see? So by using the definition, well, delta x there, imagine that is h. So imagine that delta x is kind of h. So remember that f prime of 0 is the limit as h approaches 0 of f of x plus h. So this is lim minus f of x, everything over h. So that delta x is h. So if we take the limit, if we apply the definition, we have this limit here. But now we have a problem because we need to say the absolute value of delta x or the absolute value of h. Well, by the definition of the absolute value, let me remind you that the absolute value of a number, so the absolute value of h is plus h if h is positive, and negative h if h is negative. All right, as you can see here with delta x, right, this is the same thing as this one here. Right, goes here and here. So once we write this explicitly and we consider the one-sided limits, we will have, let's consider the left-hand side limit, right? Basically, when delta x approaches 0 from the left, so this means delta x approaches 0, but with delta x less than 0. Well, if delta x is less than 0, by the definition, you see, we're going to take this guy. So the absolute value of delta x will become negative delta x. So the limit will be the limit as delta x approaches 0 from the left of the quotient between negative delta x over delta x. And this, of course, they will just cancel, and this will be negative 1. The same thing I can do when delta x approaches 0 from the right, and this will be delta x over delta x, which is 1. And guess what? As far as I'm concerned, these two numbers are not equal. So in other words, the left hand and the right hand limit, they're not the same. So the limit does not exist. So the function is not differentiable at x equals 0. So, or the derivative does not exist at x equals 0. Is it clear? Any questions? Is it about this example? Like I said, the main philosophy here is just to take the left-hand limit and the right-hand limit, and that's it. They don't agree, game over. There's nothing else you could say. All right. And now let me talk, so that was the corner point. So like I said, we have 3 examples. What about, so this is when the two limits do not agree with each other. So the left-hand limit does not agree with the right-hand limit. But what about, we also have when we have a vertical tangent line. And the main example we have here is this guy, f of x. So again, f of x is the cube root of x. And in this case, as you can see, right, f prime is not even defined. Well, I'm talking about at the point 0. So keep that in mind. It's not like you can compute the derivative of the cube root, but at x equals 0, you'll have some problems. even when you compute it, well, we haven't learned the basic rules for computing the derivative of a function, but once we learn about this, you will see that you will have the quotient of two functions, and then you have a problem with the denominator because it might be 0. So this is where you do have a problem at the origin. So the derivative is not even defined at x equals 0 for this function. So this is where we have a vertical tangent line. You see, we have a vertical tangent line. Look here. And the third one will be point of discontinuity. So in other words, there is something amazing here that happens, and that is that differentiability always implies continuity. Not the other way around, though. It's not true. Not every continuous function is differentiable, but differentiability implies continuity. In other words, so let's do this logic exercise. If P implies Q, then non-Q implies non-P. So if we negate continuity, this implies the negation of differentiability. So a function which is not continuous, so not continuous, implies not differentiable. So there is no way you will find a function which is not continuous such that f is differentiable. And look here, point of discontinuity. Let's look at these two graphs. You see here we have a hole, right, at the point 2. And the same happens here as well with these two graphs. You see they have, here it has a hole at this point, whatever it is, but at the same point, it also has a hole. So these two functions are not differentiable because they're not even continuous at that point. So this one is a piecewise, this function here is a piecewise function. You see, it has the value 2, which is 4, but here this line it excludes the point x equals 2 for each x is 2. So these functions are not even continuous at that particular point, right? In this case it's 2, and here whatever it is, God knows what it is, the point here, right? So these are the three types of where we will have a function which is not differentiable at a certain point. Okay, I think I'm gonna stop here. I think, well, it was a little bit, well, it was a bit much, but I hope you got the main idea of what happens. Next time I will talk about rules of differentiation, because it's not very productive for you to start computing derivatives using just the definition, because it will take forever. Well, we have seen some pretty easy cases, like, well, easy. Even with when you compute the derivative of the square root using the definition, right? It was a little bit of work, but once you have these rules, everything will just follow immediately. Well, the only thing is that you need to remember these rules. Okay, I'm gonna stop here. So in 15 minutes, I'll have my office hours. I see you guys have a group me. Am I invited to this group me, or it's only for you, huh? So the instructors are not invited. Anyway, I'll leave it to you. If you want to gossip there about me, it's fine. So I will stop here, and next time I will talk about derivative rules and how to compute derivatives of elementary functions. All right, so I'll see you at the office hours. Those of you who want to stop by, I'll have office hours in like 15 minutes. All right, guys, take care. Bye-bye.